Gerard. I'm part of the Blue Group, and we have the lower part of the voltage system. Also in my team is Raymond Butts and Stephen Maxson. First, I'm going to go over the system. I'm going to give its description. I'm going to show you our steady-state operating curve and some of our step response. Then I'm going to go over the first order plus dead time theory, the first order plus dead time modeling theory. Then I'm going to talk about our results, and then I'm going to conclude. Here is a diagram of our system. From the computer, it goes through some power transmitters and power recording controller to a 5 horsepower motor where it generates that power. That power goes to the generator where it gets turned into electrical energy, which then lights up the light bulbs, and that voltage is read by the voltage recording transmitter, which gets sent back to the computer and to the user. Here's a block diagram of the voltage system. Basically, we have an input of mechanical power, and it goes through the system, and we get an output in voltage. Here's one of our steady-state operating curve trials. To get the steady-state operating curve, you have to run a bunch of trials with different percentages and get the average of this section when the system reaches a steady state. You put all this together and you get this graph, our steady-state operating curve, which some of you have said is really weird, and it is. It's divided up into 3 sections. The section with the red line is mine, the green section is Ray's, and the orange section is Stephen's. They each have a slope next to them. First order plus dead time theory, you get that by analyzing the step up and step down graphs. And from the graph, you get the dead time, the gain of the system, and the time constant of the system. Here's one of our step up runs. All the different colored lines, the purple, the orange, the green, are all part of the analysis required to get the dead time, tau, and the gain of the system. Here's one of our step-down functions. All the different colors also are part of the analysis. And as you can see in the light green, which may be hard to see, there's the T0 equals 0.24. The gain of the system equals negative 0.2, and the time constant is 0.3. Here are our results from our step-up system for the time constant. You can see that Stephen didn't have a very big tau. I was kind of in the middle, and Ray was higher than both of us. Here's the step-down averages of tau. Instead of for each run, they're just averaged. I had the highest tau, Stephen had the middle, and Ray had the smallest, and there are error bars on there except for Ray's. Here is the system gain. This kind of relates, you can see this by looking at the steady-state operating curve. Because my part of the curve is very flat, I didn't have much gain. Ray's was pretty much vertical, so he had more gain than Stephen and I, and Stephen's somewhere in the middle. Here's the averages for our gain for the step down. Again, I had very little. Ray had a little less than Stephen, and Stephen had the most. So here are the different dead times of the system. We all generally had less than 1, except for Ray on run 2. I don't know why that was happening. Here are the averages of T0. Stephen's was 0, which is why he doesn't have a bar. Mine was about 0.2, and Ray's was a little over 0.1. The first order plus dead time modeling theory gives you that equation at the top, and it helps you be able to model basically what's on your step up and step down graphs. To get that, you need to know the dead time, the step height, the gain, the dead time, the time constant, the input baseline, and the output baseline. These are the parameters that I used graph that is coming up. This is my step-up FOPT experimental versus model graph. The purple and blue are what we got from running the system on through the actual system, while red and green are the model. So it's pretty close. So here's one of Steven's step downs. It is a little prettier than mine, so I used it. The blue and the red are the experimental, which we got through running through the actual system, while the green and the purple are what we got from the equation. The problem with the modeling is you can't get this part of the graph very easily. It has to come in straight from there. So here are the results. The next slide will show a graphical representation of this. But you can see for step up is in the blue on the right, and step down for each is on the left. And then the experimental parameters are on the top, and the model parameters, which we got from the equation, are on the bottom. So this is the exact same data except in bar chart form. And in general, the gain and the dead time are about the same. This is for my part of the system. But my model tau for both my step up and step down were about 3 seconds greater than my experimental data. Here is Ray's results from his part of the curve. And once again, on the right in the blue are the step ups, and black on the left are the step downs. The top is what we got from running the experiments, and the bottom is from the model equation. Once again, there is some variation, like in his case step up and tau step up. But most of the time, they're about the same between the model and the experiment data. This is Steven's section. And again, he has 5.28 plus or minus 0.29 for a step up that he got from the experiment, while he got 5.75 from his model. And on his dead time, he has 0 seconds for his model, and also 0 seconds for his experimental on the step down. Again, Steven had a little bit more variation than me and Ray. So some of his are a little off and not perfectly straight, except for T0, which was close to 0. The voltage system, it's a little funny. One of the things, it kind of bounces around a lot. I couldn't really get a good picture, so I just kind of used this one, but you can see how some of the dots go down. And in the very end part of my part of the system and Ray's system, you can run the experiment with the same input percentage but get a different output, which was kind of a pain. Another thing that's funny about the system is when you're doing step up and step downs require more input than step up to get the same change in voltage. Conclusion. The first order plus dead time modeling of voltage system can help you make a mathematical equation from step up and step down data first. And that can help you if you need to give a customer some information so you can change different parameters and